Section 9.4, Newton's second law for rotational motion about a fixed axis. So once again, we are back to Newton's second law. I told you this would keep popping up again and again and again, and here we are, right? So if we go back to F equals ma, force equals mass times acceleration, we're going to focus in on the tangential force and the tangential acceleration, because we want to think about some sort of circular motion. Like here's an example of a boy swinging a glider in a circle, right? The plane on a string, round and round. So if we want to know what's causing that angular acceleration, if we want to write this in terms of torque, we could start with this tangential force and thus the tangential acceleration of the plane swinging round. That's our linear version, but now we want to switch to the angular version. So we remember that torque is the tangential force times the lever arm. The lever arm in this case would be the distance from the axis of rotation, which is the boy. So that would just be the radius r. So we could then write that our tangential force is the torque divided by r, divided by the radius. Similarly, the tangential acceleration is related to the angular acceleration if we just multiply the angular acceleration by r. So if we plug in r alpha into this equation, and if we plug in tau over r on the left side, multiply the r across, we arrive at this equation on the bottom, that the torque is equal to mass times the radius squared times alpha. And we're going to define this quantity in parentheses, m times r squared, as the moment of inertia. And that's with a capital I. And we'll see more about that in a moment. So this is true for any time we have a single object that is traveling in this rotational motion, a single mass m at some distance r from the axis of rotation. We're able to calculate the moment of inertia. What if we instead have a more interesting object, right? Something that isn't just a single mass, but has some sort of length and mass spread around it. Well, in this case, we're going to need to sum up all of the different masses and how far they are from the axis of rotation. So we could say, hey, look, this shape, there's a mass 1 that's in the midst of this, and it's at some distance r1 from the axis of rotation. Oh, and there's also this other mass way over here, mass 2, and it's at some distance r2. We can do the same thing with mass 3, mass 4. And so we're going to sum up the torque that each of those masses adds up to create the net torque of this funny shape. So the net external torque is going to be the sum of all of those masses times their distance from the axis of rotation squared, and then that is multiplied by the angular acceleration. Because notice the angular acceleration will be the same for all of them. They're all sweeping through the same angle in the same time interval. They might have different tangential accelerations, but the angular acceleration will indeed be the same. This now introduces our rotational version of Newton's second law. So the rotational analog of Newton's second law for a rigid body, something that can't wiggle, rotating about a fixed axis, is that the net external torque is equal to the moment of inertia I times the angular acceleration. So this is our F equals ma. It's just now torque equals I alpha. This is a really useful equation. This is why when we have a balance of forces and a balance of torques, we set the angular acceleration equal to 0, and then the sum of the torques, the net torque, is 0. Well, the angular acceleration is not always 0, and so now we have an equation for if there is angular acceleration as if something is rotating. So this is, as you can imagine, a very big and useful equation. It's a good framework. This I is the moment of inertia, and if you have a system of masses, of individual mass particles, like balls, right? Little point particles floating through space, then you can just sum up the rotational inertia by taking the mass times the distance from whatever your axis of rotation is squared. And so you'd add that one, and then there'd be some rotational inertia from this object. And we'll look at an example of this in just a moment. before we get to that, one note is that the angular acceleration must be expressed in units of radians per second squared. That is our SI unit. And if you instead did revolutions per second squared, then the numbers wouldn't work out. You wouldn't get the right answer. So note that we need those units, and we'll also jot down this equation for I. That's another good one to add to your sheet for a system of particles. All right, and we'll see an example for when it's a full rigid shape in just a moment. But first, let's think about this system of particles and how we can use this I equation for it, the moment of inertia. So example 9, the moment of inertia depends on where the axis is. Two particles each have mass m and are fixed at the ends of a thin rigid rod whose mass can be ignored. Very small mass compared to the two particles. The length of the rod is L. Find the moment of inertia when the object rotates relative to an axis that is perpendicular to the rod at A, one end, and B, the center. Right. So part of the challenge here is even picturing what's going on. So we have this thin rod that's really just a connecting point between two particles, each of mass m. Those are the important parts of the picture. We have these two masses m. What's different between A and B? Well, in A, it says that the object rotates relative to an axis that's perpendicular to the rod at one end. So we could take one end of the rod, like this left end, and the axis needs to be perpendicular to the rod. So if the rod, I drew it horizontally, so that means my axis is going to need to be in the vertical direction. So that would be then my axis of rotation. Right? Versus, and this is for part A. For part B, notice it says relative to an axis that's perpendicular to the rod at the center. At the center, that's now going to be between the two masses. So this is in case B. The axis of rotation. Notice we aren't changing the masses themselves or the rod that's connecting them. We're just changing the rotation point, the fixed point that everything else is rotating around. So how does this influence things? Well, we can calculate the moment of inertia using that equation that I is the sum of the masses times their distances squared. So let's take a look. For A, we have this equation, sum of mr squared. So we have one of our masses is m1 times r1 squared. Great. And then the second mass we'll call m2. So m2 times r2 squared. And these r's are the distance from the axis to the mass. So r1 is just 0 because the axis is passing right through mass 1. r2 is L because it's the full length away from the axis. And the masses in this example are equal to each other. So m1 is equal to m2, they're both just m. So if we plug in those for m, so they have the same m, we have 0 and L squared, we find that our moment of inertia is just mL squared for case A. What about for case B? We know in case B, it's the same masses, and so we haven't actually changed the physical setup, just the pivot point. Is that enough for anything else to change? Well, we can take a look. So as we look at this, we notice the masses are still the same, but the radii, r1 and r2, are different. Instead of being 0 and L, it's r over 2 for L over 2 for each of them, right? Each of them are halfway from the center of the rod to the masses. Now, when we plug that in, because this is squared, we aren't going to get the same result as we got above. L over 2 squared becomes L over 4. So ml over 4 plus ml over 4 becomes ml over 2, or I is equal to 1/2 ml squared. This means there's half the rotational inertia in case B as there is in case A. Why is that? Well, the rotational inertia tells you how hard it is to rotate an object, and it's easier to rotate something when your mass is close to the axis of rotation, even if you have two that are closer versus one that's much further away. When you have one that's much further away, it sweeps out a larger circle, and there's more resistance to that rotation. And that's what the moment of inertia is trying to convey. It's our rotational equivalent of mass. So it's how much the object is resisting rotation. I like to demonstrate this sometimes with, you could get like a rod, right? And it's easier to turn it from the middle, right, where the mass isn't too far on either extreme, versus if you try and do it from one end, this is a lot more work. There's more resistance to my rotation. So that helps to illustrate this. Now this is getting into an object, right? This is no longer point masses or particles like we had in this example. And it turns out when you have an object like a rod that you do care the mass is not negligible and you want to find its moment of inertia, we have something that can help us out. So there's this table 9.1 that has the moment of inertia for various rigid objects of mass big M. This is something that's provided for you on exams, so you just have to know how to use it. That if you have an object that's rotating, you might need to know its moment of inertia, and so then you can look it up in the table, and you'll have to figure out which object you do want. Because notice there are some similar ones, like if we talk about our thin rod, there's a thin rod with the axis perpendicular to the rod and passing through the center, right? And that has a rotational moment of inertia of 1/12 ml squared. Versus you could have a thin rod with the axis perpendicular to the rod passing through one end. And this one is 1/3 ml squared. So that's 4 times bigger than if you're rotating it from the middle. It's significantly larger moment of inertia. So where the axis is located makes a big difference with your moment of inertia. We also have some other objects in here. There's a solid sphere with the axis through the center, solid sphere with the axis along one edge of the surface, a shell, a solid cylinder, or a disc, either one, which is a useful thing to note. And then thin-walled hollow cylinder or hoop, right, where you just have the outer hoop going on the outer edge, and then some thin rectangular sheets with a couple of different axes shown in red there. Right, so this introduces the idea of Newton's second law for rotational motion, where we have the net torque, where torque causes an angular acceleration. Net torque is equal to that angular acceleration times the moment of inertia, where moment of inertia tells you how much the object or the particles resist the rotation. We'll wrap up this section right there.